Hello to everyone. I'm America Califano from the University of Padua, and today I'm showing you some very preliminary results about the mechanical behavior of Ti6Al4V laser welded single lap joint. We all know that laser welding technique has superior characteristics if compared to traditional welding techniques. As a matter of fact, laser welding allows to reach very reduced distortions in the final component, reduce dimensions of the heat affected zone, high precision and high speed. For these reasons, the laser welding technique is very appealing for the sectors of aerospace and aeronautics, where often there is the need of joining components and subcomponents made in TI based alloys. However, if on one hand, laser welding technique allows to reach very high levels of precision, on the other hand, it has a high cost. That's why there's the need of deepening the knowledge about the mechanical behavior of joints obtained with this particular technique. In this case, the case studies are single lap joints in Ti6Al4V alloy. Here you can see a schematization of a single lap joint that has been obtained by joining two plates with a thickness of 3 millimeters each, and the overlapping zone has a length of 30 millimeters. Different single lap joints have been obtained by varying the laser welding parameters. In particular, 6 classes of joints identified with the letters going from A to F have been obtained. Each class is characterized by a turn of the welding parameters that are laser power, laser speed, and laser focus. In particular, laser power is constant and equal to 3 kilowatts, while the laser speed varies from 30 to 40 millimeters per second, and in detail, class A and D, B and E, C and F share the same speed, that is 30, 35, and 40 millimeters per second, respectively. While concerning the laser focus, the first 3 classes share a superficial laser focus, while the last 3 classes share negative defocus of the laser beam. 2 joints for each class have been obtained, and these joints are identified as A1, A2, B1, B2, and so on. From each joint, 7 specimens have been obtained. They have been cut out from the joint perpendicularly to the welding bead. So this means that 14 specimens were obtained for each class, but only 6 specimens, 1 for each class, have been considered for the experimental tests. These specimens are identified as 1A1, 1B1, 1C1, and so on. So this nomenclature means that this is the specimen 1 from the joint A1. Here in this picture, you can see a schematization of a specimen equipped with 2 strain gauges, E1 and E2. E1 was glued on the same face as the welding bead, while E2 was glued on the opposite face. So here you can see even a picture of an actual specimen equipped with the 2 strain gauges. While here on the right, you can see the tensile test machine belonging to the machine design laboratory of the University of Salerno. This machine is an MTS inside 30 machine with a load cell of 30 kilonewtons, and it was used for carrying out static tensile tests. We all know that single lap joints, when subjected to tensile tests, tend to bend in correspondence of the overlapping area. And here you can see a schematization of this behavior, while on the right there's a picture of an actual specimen mounted inside the machine and bended just before failure. So due to this bending, the strain gauges mainly measured compressive strains. As a matter of fact, here you can see an example of load strain curves for the specimen 1C1. So you have here the 2 curves for the 2 strain gauges, and you can see that the curves are quite in agreement with each other. Please note that on the x-axis we have the absolute values of compressive strains. If we compare the curves obtained by E1 and E2 for the 6 specimens, we notice that the behaviors are quite different. As a matter of fact, in the first case, so for the curves obtained by means of E1, we can see that for all the specimens, the curves are quite in agreement, so the strains do not differ from each other. Well, if we take a look at the curves obtained by means of E2, the curves are not in agreement, so they diverge. This behavior has to be found in the fact that E2 was glued on the face opposite to the welding bead. And as the different welding parameters lead clearly to different welding penetration lengths, so on the face of E2, the measured strains were very different from each other, so for the different specimens due to the different welding parameters. And this behavior can be noticed even taking a look at the pictures of the fracture surfaces reported here on the right. Even if these pictures are not high quality, we can see that the width of the fracture surfaces are not constant. In particular, if we focus on the last three specimens, so 1D1, 1E1, and 1F1, we can see how going from D to F, the width of the fracture surface is thinner. This behavior is linked to the different speed used during the welding technique. As a matter of fact, we can see that going from D to F, the laser speed is increasing. This means that with increasing the laser speed, the welding penetration is smaller, and so the specimen is weaker. This behavior can be even seen in the load displacement curves reported here. So we can see here the first three curves for the first three specimens, while here the curves for the last three specimens. If we focus on the first three, so on the curves for the specimens A, B, and C, we can notice how with increasing the laser speed, the maximum load to failure decreases. So increasing the laser speed is linked to weaker specimens. In conclusion, in this study, there are very preliminary investigations about the mechanical behavior of Ti6Al4V laser welded single lap joints. In particular, 6 specimens have been considered and subjected to static tensile tests. They were obtained from single lap joints that were obtained by varying laser power, laser speed, and laser focus. Each specimen was equipped with 2 strain gauges, subjected to tensile tests, and load strain and load displacement curves show that there is a clear dependence between the mechanical behavior and the welding parameters. In particular, the strongest specimen is the one that has been obtained from the joint with the lowest laser speed, that is 30 millimeters per second, and with a superficial laser focus. Near future investigations will first of all deal with metallographic analysis of the fracture surfaces in order to better link the characteristics of the fracture surfaces to the welding parameters. Then the remaining virgin specimens will be subjected to fatigue tests. And finally, finite element simulations will be carried out as well for investigating further conditions and scenarios. Thank you for your kind attention.